a solution, and so I want to try to write the solution on the disk for Laplace's equation based on the solution for the half plane. Solution for the half plane for Laplace's equation. Remember, like I was just saying, we've got phi equals to 0 here, and we've got phi equals to pi over here, because we're using arg sub 0, right, that argument. So how do I do it? What do I need? So I think I need this over here. I need the inverse map, yeah? So I need to say that this is actually phi of H inverse of W, right? So in order to complete this example, I need to find the inverse. We can do that, though. See, we got W equals to, that'd be good practice for us, Z minus I over Z plus I. Can we find the inverse map here? What do you have to do to find the inverse? If this is H of Z, right? Yeah, solve this for Z, and that will find you H inverse of W. So I have W times Z plus I equals to Z minus I, which gives me WZ minus Z is equal to minus IW minus I, which gives me Z Z times W minus 1 is equal to, minus IW minus I, which gives me Z is equal to IW plus I divided by 1 minus W. Or if you like, I times W plus 1 divided by 1 minus W. So this is literally phi of I times, don't do that to me again, you punk, 1 minus W. A formula for this, by the way, is inverse cotangent of x over y. That will be an element of 0 to pi, not inclusive, because that's the inverse cotangent I use. So there's a stone-cold formula for the arg sub 0 in the upper half plane. And so to actually put this into practice, we'd actually have to work out what this is in terms of, so, all right, so we want, just inverse cotangent, right? Of, x over y, where, x plus iy is equal to I times W plus 1 over 1 minus W. How do we work that out? Let's work it out. So I'll do it over here. So I've got I times W plus 1 over 1 minus W. So that's I times U plus IV plus 1 divided by 1 minus U minus IV. You gotta make the denominator behave. How should we make that happen? So we multiply by the conjugate, right? So we just gotta multiply this by 1 minus U plus IV, 1 minus u plus iv. Let's see here. So downstairs, I'm just going to have 1 minus u quantity squared plus v squared. Don't be a punk and actually multiply it out. Think through it, you know? Just saying. Understand what complex conjugation multiplication does. It gives you the magnitude of the denominator, right? So what's the magnitude of my denominator? It's this plus that, right? Squared. Upstairs, I've got, you know, I guess I'll do one more step here, clean it up a bit. This is minus v plus I times what? U plus 1, right? I think it's worth doing that step before I multiply. Over here, I've got 1 minus u plus iv. All right? So I multiply real and real and imaginary and imaginary. I do not distribute through like everything, you know? So that gives me minus v times 1 minus u minus v times u plus 1, that's my real part, plus I times, well, minus v squared apparently, and then plus u plus 1 times 1 minus u, if I haven't made a mistake, divided by 1 minus u squared, which I kind of like that being u minus 1 squared. It just looks better to me. So, and then how does this simplify? It's got to have some simplification, I think. You notice you got a plus uv here, you got a minus uv here, so those be canceling. And then you got a minus v, minus, so I got a minus 2v from all that, and then plus I times what? Minus v squared minus u squared plus 1. Cross terms, they be canceling, right? You agree? Agree? And then, of course, the denominator still what it was. So, lo and behold, we have figured out that x is equal to minus 2v divided by u minus 1 squared plus v squared. And we found that y is equal to 1 minus u squared minus v squared divided by u minus 1 squared plus v squared, right? Now let's put it all together, because now we can write down the solution to Laplace's equation on the disk here, right? So what is it? This kind of thing always happens with these calculations, guys. Like, you get this perhaps ugly denominator, right? And the denominator, it does things. Like when u equals 1 and v equals 0, the denominator blows up, right? That's here. This is 1, 0. That's where the denominator is not defined, right? And so you notice that when you take the fraction of x over y here, the denominators cancel, and what are you left with? Inverse cotangent of, well, minus 2v divided by 1 minus u squared minus v squared, right? Which I could rewrite as inverse cotangent of 2v over u squared plus v squared minus 1. I think that would be easier to understand. That is a solution to Laplace's equation on the unit disk in the w plane. All right, and I finally circle back to my original picture from last class where I showed you we could make the technique go both ways. You see, I've ripped the solution from the z plane and moved it over to the w plane this time instead. I had to find the inverse map to make that happen. But it's interesting to think about how this works. How does this work? Inverse cotangent. How does inverse cotangent work? So like inverse cotangent of 0 is 0. and oh, sorry, I have to think. Cotangent, my bad. Sorry, guys. If this is theta, this is x, and this is y. Cotangent theta is what? Is it y?
No, it's
X over y, right? Yeah.
I was thinking it's
You're thinking of tangent.
yeah.
Okay, so what's the deal with that? We should be able to understand. All right, so like so this u squared minus u squared plus v squared minus 1, this approaches infinity, right, as you go to the edge of the disk. See that? So this, this approaches 0 as you go to the edge of the disk, which makes this either go to, essentially you're going to get like cotangent, inverse cotangent of minus infinity down here, and inverse cotangent of plus infinity up here. And you're like, oh, now you've got plus and minus infinity, huh? I see how it is, right? Yeah, I know, it's hypocritical. What can I tell you? This infinity is not the same infinity we were talking about before. This is the infinity in the limiting sense of the real function inverse cotangent. Fair enough. It is not the one-point compactification of the complex plane. You got me. It's true. If I understood my inverse cotangent better, I should be able to explain to you that, one of these is, well, this one goes to 1, and that one goes to pi. Yeah. So I guess I'll just have to graph cotangent for you. Cotangent is cotangent theta. That's probably the fastest way for me to convince myself I know what I'm saying. Cosine theta over sine theta, right? So the inverse cotangent that I believe in is the inverse. Well, there's a choice, and Euler made a different choice. So who am I to say, But I believe it looks like this. All right, that's pi over 2. It's 0 at pi over 2. And it's got like this. This is the graph of cotangent. So the inverse cotangent relative to that branch, you flip the graph, right? You flip the graph, and the vertical asymptotes become horizontal asymptotes at 0 and pi respectively. And it oh man. So if I could do math here. I can't even see how to flip the graph at the moment. I am not operating with a full tank. Will you finish the graph? So the thing I was scanning a couple minutes ago, well, I guess we're out of time, so I won't show you that, but I will try to have a PDF of the thing I sent you guys the video to. Like I told you, I need to, well, I can scan the paper I have. It just doesn't have color, so I'm kind of discontent. If you guys have questions about the quiz, which is take home, you can ask me whenever you can find me, I suppose.